Hi, my name is Matt Holliday and welcome back to my class on Programming in Go. So this is going to be my third segment on object-oriented programming. The first one we talked about methods and interfaces, and the second one we talked about composition. In this one, I want to drill down a bit into some details, some picky details about how things work, and then I'm going to wrap up talking a little bit about the pragmatics of how we use interfaces. So the first thing I want to do is talk about what a nil interface is. Okay, we've talked about other aspects of interfaces, but if you create a variable of interface type, what value does it have by default, right? For ints, it's 0. For strings, it's the empty string. For interfaces, it's nil, but nil means something a little different. And to explain that, I need to drill down into how an interface works under the hood. Okay, because an interface really has two parts. It has to have some way of referring to the actual concrete type, the value. But we also need to capture what type that value is. So it has two things in it, and we can really think of them as two pointers, right? So if I have this variable right here, okay, R is a variable of interface type right now. It's io.reader. I haven't put anything into it, so its value is nil, and B is a pointer to a byte buffer. But what's interesting is that if I assign B to R, if I assign the nil pointer into this interface variable, R is not nil anymore. And that's a little bit counterintuitive. And so I want to show why that happens. And to do that, I'm going to have a picture, right? I had pictures for things like slice descriptors and string descriptors. I'm going to have a picture for an interface. Because an interface has two parts again. It has something that represents the type, and it has a pointer to an actual object, the concrete data, a value, right? If both of those pointers are nil, the interface itself is nil. So this is the original R, and it has a value. If we compared R to nil, that would be true, okay? R prime is subtly different. The pointer to the value is still nil because we assigned it this B, but B was equal to nil, the nil pointer, okay? So the value part of this is nil, but notice over here, the type part is not nil anymore. So this interface now says, instead of being nil, uninitialized, I have a nil buffer pointer, and I know it's a pointer to a type buffer. Okay, let me go back, right? R is nil when it starts. B is a pointer to a buffer. And nil is just another value. There's nothing magic about it. So it's a nil pointer, but it's a nil pointer in a sense of type pointing to a byte stop buffer. And so when I do this assignment, right, it has a value, a nil pointer to a buffer. Okay, and that's okay. Remember in the last segment, we had this example of the int list, which used pointers. It's a linked list with pointers, and we called methods where the receiver could be nil, and that's acceptable, and it's acceptable here. We could call a method on R that, when the method gets called, it's up to the method to decide how to handle the fact that the receiver is a nil pointer, and that might be okay. If you called length, it might just say nil pointer, return 0, because that makes sense. If you tried to read values out of it, then it would panic and die because there wouldn't be any values. But taking the length of it is okay. So calling a length method, if there were a length method, on a nil pointer is okay. So it makes perfect sense from the point of view of the programming language to allow an interface to have a nil pointer. But it's no longer nil in the sense of an interface is nil. The interface variable is nil when it's in the uninitialized state, okay? Both the pointer and the type are nil. And anytime you put either a type into it, well, you can't put a value without a type. So anything you assign to it, whether it's a nil pointer or a non-nil pointer or an integer, the type will be set. So it'll always have a type even if the value is nil, right? But in any case, this second case of R prime, the R prime over here, after we do this assignment, the interface is not nil. Okay, so I want to show the example where this actually practically matters, because right now you're saying this is very abstract, But actually, it comes back to bite people in the butt on a regular basis. And it does so because we need to talk about the error type. The error type, again, in the beginning we said, hey, we're not going to explain what error is. We'll just treat it like a primitive type. It's either nil or not. Okay? But actually, error is an interface. It's an interface with one method. The method is error that returns some sort of string describing what the error is. So of course, if I have a var error of type error, right? If I don't initialize it with anything, it's nil. And we've been saying things like if error is equal to nil or not. Actually, what we've really been saying is, if error is not nil, that means an error happened because this error interface is no longer uninitialized. It has an error in it of some sort. Now, the reason it's an interface is because sometimes we customize errors. Okay? I mean, I could just say, hey, an error is always a string. Just shove a string into the error and be done with it. But then you go look at certain kinds of errors where you want to report more information. So you have some sort of type, it encapsulates a bit more knowledge, or in some cases, people want errors with a traceback. And there are ways of creating errors with a traceback, not using the standard library, but using some extension packages, right? So our error thing, the actual value that's in the error, might be more complicated than a string. It might have other data. And when you call the error method, well, then it goes and looks at that data and figures out how to format it into a printable string. Great. Okay. So again, how do we figure out if an error happened? We compare the error interface to nil. If it's nil, nothing's ever been put into it, there's no error. Now, I want to take this slide and bring it over into the playground. Okay, because I want to run this. So if I look at this, I've created a custom error type. And it's typical to start with the letters ERR and then something, error foo in this case. It has the actual error in it plus maybe a string to represent a path. And I've defined an error method. Once I do that, error foo is going to be compatible with the underlying error type. Okay, so I format a string and return it, that's fine. Now I have a little function, and my function doesn't do anything useful. It returns something, right? But it returns this concrete pointer to an error foo. All right? This is a mistake, right? And I'm going to return nil, which is a nil pointer. But it's not nil in the interface sense, it's nil in the pointer to error foo sense. So when I get down to my main program, right, I initialize this variable error. Now, there's a reason, right, I could do this. Right? If I did this on this first line right here that's commented out, if I did this, error would be star error foo. It wouldn't actually be an error interface, right? If I did this line 21 that I've commented out, error would be a pointer to an error foo. And that's not how we usually do errors though, right? We usually do errors by having some sort of variable that's declared to be of type error, which means it's declared to be an interface type. So now I'm assigning to it. Let's see what happens when I run the program. Oops. Why? Because XYZ returns a nil pointer to a concrete value, and that gets copied into an interface, and the interface is no longer nil. It's not nil even though it has a nil pointer inside. So we print oops. And the fix to this, for example, would be to change error XYZ to return a type of error. And now when it returns nil, it's not returning a nil pointer to a concrete type. It's returning a nil interface value. And now my code works because my intention is I'm not returning any error. Okay. And so this is an example where if I accidentally put a nil concrete pointer into an interface, the interface is non-nil. And because of the way we use error, right, the common paradigm is we don't check to see what's in the error. We just ask, is the error nil or not? Okay. Now, differentiating between the interface being nil and the interface having a nil pointer is actually not easy. And I'm not going to go there because it takes some tricky code that's just not the kind of code we want to write. The correct approach to this is to avoid, in the case of error specifically, returning concrete error types in nil, right? This is the case where we really want our function to return the interface. And nil then, when we return nil, has the right meaning. It means the nil interface, okay? So this whole business about whether the interface is nil or not is actually meaningful because it does cause this potential problem with how we deal with errors. So now I want to go back to the slides because I want to talk about something else. And I've already talked about this. What's on this slide you've already seen, the notion of pointer receivers and value receivers, but I want to drill down to it a bit more. Okay, so I have my point structure and I have my add method. So the add method changes the point, right? Because it takes a pointer receiver and so the actual point gets changed. But my offset of just returns values without changing point. The receiver does not change because it's copied in. I copied in, do something with the values, and ignore it, right? And of course, you cannot overload the methods with both a pointer and a non-pointer type, right? So your method either takes a pointer receiver or it takes a value receiver, but not both. Now, the first thing that's interesting in Go is that just like with structs, right? If I had a pointer to a struct, I could say p dot some field name like p dot x, and I didn't have to put a bunch of extra stuff on it. All right? Go is fairly smart about figuring out how to call your method. Right? So assuming we have what was on the last slide with the points, right? If p1 is a pointer to a point, and p2 is an actual point value, right? Then calling offset of is fine, for example, in p1, because the compiler will translate p1 into the dereference the pointer p1 and then call the method. Okay? And p2.add is fine. Add, remember, took a pointer, but p2 is a variable of type point. It has a real place. And so again, so the compiler can again translate that and say, fine, take p2, take its address, and call the method with the pointer. Okay? So the compiler can, in most cases, automatically solve this issue. You just say p1 dot something or p2 dot something, and the compiler will figure out how to deal with the pointer receiver or the value receiver. Okay? Under the covers, it'll either do a dereference or take the address of operator for you. That's fine. But the catch is, of course, the ampersand operator only works on something addressable. So I want to bring into this discussion some terms that probably aren't used in Go that much, but they're used a lot when talking about other languages. And it's the notion of L value and R value. And I'm going to make this real simple, right? If I have an assignment, an L value is something that can appear on the left-hand side of an assignment statement, which really means it's a place you can put something. An R value is just a value. And by R value, it's something that we say can only appear on the right-hand side. Okay, an L value could appear on either side, but only an L value can be left of the equal sign, and an R value has to be on the right-hand side of an equal sign. Because an R value is like a number, 1. Well, you can't assign something to the number 1 because the number 1 is just a literal 1. It's a value that doesn't have a place. Okay? So I have this table here, and nobody else has really made this table. I think this table is useful for you because it says that pretty much everything works in terms of combining pointer receivers and value receivers with pointers and values, except for one case, okay, that I've brought out before. There's two cases where it just works the way it should, and there's 2 cases where it works because the compiler changes it. Actually, there's a third case where it just works, an R value with a value receiver. Okay, so 5 out of 6 cases, it either just works or the compiler knows how to do it right by taking the address or dereferencing the pointer. But there's one case that can't work. Okay, and so down here I have this variable p of type point. Okay, and I can add to it, that's fine. But the second case is trying to do the same thing with a point literal, and that fails. Because the point literal is not a variable, it's not a place. It's a value that's sort of disconnected. All right, and so when I try to add to it, I need to take the address of it, but I can't. There's no way to take the address of an R value. You can't do it. And so that's not going to compile. All right, so, you know, the number 1 is an R value, a string ABC is an R value, right? And a literal like this is an R value. It's a value that doesn't have a place. It can be on the right-hand side of the assignment statement, and because of that, or I should say, it can only be on the right-hand side of an assignment statement. It's not addressable. The address of operator cannot be applied to it, and so you cannot call a method that has a pointer receiver on one of those values. I just beat it to death. I think I've said the same thing 3 times now, but I just want to get this clear because this is a little thing that's going to trip people up. Now, the other thing, and we talked about pointer versus value semantics or reference versus value semantics. They come into play again when we talk about pointer receivers. All right? And one of the things we said about pointers is sometimes we have to use pointers for things that cannot be copied. And the same thing applies to a method. If I have a type, and buffer is exactly that kind of type, okay? Because buffer has inside of it an embedded slice. Well, if I make a copy, that copy may not be safe. And this also is true for things that have an embedded mutex and so on, right? And so here's the thing. All of our methods are going to have pointer receivers because it's not safe to make a copy of the buffer, right? And so there's a notion of consistency, right? If one method of a type takes a pointer receiver, then in general, all the methods of the type should take a pointer receiver, okay? And then I have a little exclusion down here, well, except when there's a really good reason not to. But in general, if you have a type like this, particularly a type where it's not safe to be copied, then your methods are going to take pointers, and they should probably all take pointers to help reinforce that notion and save you from the mistake of accidentally writing one where you copy the not copyable thing and then everything stops working. And now for something completely different. Okay, I want to talk about method values, but before I can talk about method values, I need to introduce a concept. And it's really a concept from functional programming. So if you're familiar with functional programming, you'll have heard the term currying. And currying is a process in which we take a function that has, say, 3 parameters, we bind one of them, and turn it into a function that has 2 parameters. Okay? And so my example here is I have a perfectly ordinary function called add. It takes 2 integers, returns the sum. Great, not very exciting. Okay, what I'm going to do is I'm going to create another function, and my function is called add to a, right? Where I'm binding a value to a, and so I'm turning this into a new function that only takes a b value. And what does it do? Well, it adds b to whatever a was every time, right? And so my function actually returns a function. It returns a function in b that calls add with a and b, where add, of course, is closing over the original parameter that was passed into add to a, right? So if I create a function add to 1 by calling add to a with the value of 1, I get a function where whatever I pass in is being added to the number 1. And so this thing is true. If I add 1 and 2 and get 3, that's the same as calling add to 1 with the parameter 2. I don't need to pass the 1 in because the 1 was bound into my function. Okay? And again, the technical term for this is currying. Well, I'm going somewhere for a reason. And the reason is something called a method value. And I want to say this in a slightly different way. A method value is a method closed over its receiver. Okay? Now, if we think about a method, it's a special function. It has its normal parameter list, and then it has this special parameter we call the receiver. So however many parameters you have, right? So here's my function distance. It has one normal parameter, but it's in some sense, it's really a 2-parameter function because I have the regular parameter q and I have the receiver p. Okay? And what I'm going to do by making a method value is I'm going to bind something to p and turn this into a function in just the parameter q. Okay? And so in a sense, the method value will have closed over p. It'll have captured p in a sense. Right? How do I do that? Well, here are 2 points, p and q. Right? And now I have this very interesting little thing. Okay? I'm going to assign to the variable distance from p the method value of p.distance. And what that is, it's the effect of calling the distance function on p specifically. And now if I call distance from p and pass in q, this is exactly the same, well maybe it's the same, as calling p.distance with q, right? Because distance from p has captured p. So now I'm back in the playground. I've got the code from the slide, I've got the point type, I've got the distance method, I've got a couple of points, and I'm just going to print the distance the usual way. So let me run that. Okay, that's no surprise. So what I want to do now is I want to actually create this method value. And that's just the object name dot the method name. There's no parentheses. I'm not calling it. Okay. And what I want to do now is I want to ask, well, what is that? So we're going to change the print line to a printf. And we're going to use %t. And we're going to ask, what is the type? And when I run that, it tells me it's a function taking a point and returning a float. Now I'm going to compare it to something else, which is not something you usually see, right? I'm going to look at point.distance, which is the method on the type. And what that's going to say is, it's a function taking 2 points and returning a float. Now, the way we normally use it, p.distance, right? One of those is the receiver, one of those is the regular parameter. I've actually converted it now to a function taking 2 points and returning a float, right? I can now print something else. Instead of calling p.distance, I can just call distance from p and pass in q. Let me run that. I get the same value. We need to go back and talk about pointer versus value semantics, because they apply here also. Notice my distance method took a point as a value receiver. Okay, there's an implication, and that is that the distance from p value captured that value at that instant. It's been copied right then. So what happens if I change p? I'm going to get rid of this for a second. Okay. I'm going to change the value of p to have some other number. Okay. When I run this, I still get 5. And the reason I get 5 is the distance from p has copied into it right there the value of 0.11 for p. And it doesn't matter what happens to p after that. Distance from p will always use the same p that was created on line 22 because it's a value and we closed over the value. Normally, closures always close over by reference, but here's a case where we've copied the value. Now, if I change my method to be a receiver, a pointer receiver, it's going to change this behavior. Look what happens now. Okay, the first value is 5. That's with p being the value of 0.11. Now I recreate that. Okay, so what happens here is because distance takes a pointer receiver, it copies the pointer to p, not the value of p. And so now when I call distance from p down here at the bottom, I'm going to get whatever value p has right now through the pointer. This is more like a normal closure. Okay, so a method value works like a normal closure if you take a pointer receiver, but it works a little bit different. It captures the value immediately if you take a value receiver. So this slide just summarizes what I was talking about. Okay, we're going to come back to this when we do the next homework exercise. We're going to use some practical examples of method values because they actually do show up a lot, in certain contexts at least. And so we'll drill down into this a bit more. But it's very important to understand if you're going to take a method value, is it a pointer receiver or a value receiver? Okay, so now I want to drop into one last topic because I want to talk about some practical aspects of using interfaces in Go. Now, the first one we've mentioned a couple times, and that is we typically allow the consumer to create the interface definition, okay? In some languages, again, you create like an abstract-based class. So whoever creates the class says, hey, these are the methods, and these are things that people are going to need, assuming they really need them. In Go, we let the consumer say, hey, this is the minimum behavior I require. I need you to give me something I can write to. And I don't care what else it is. I don't need to worry about the other methods it may or may not have. I don't want to specify them because that leaves you, the caller, the maximum freedom, to pass me whatever you like as long as it's a writer. I don't need to know anything else but the fact that I can write to it. So again, consumers most often create the interface definitions, and then various objects satisfy them or don't. And that's why, again, we don't have an implements keyword. Now, number 2 should be obvious. Learn what interfaces are already out there. Because if you're defining a method, for example, that takes some type of interface as a parameter, if you're using one from the standard library, that's going to maximize your compatibility with the other code that's out there. The third item on the list has to do about small interfaces. And again, the smaller the interface, the better, because we have this quotation. I think it's from Rob Pike. The bigger the interface, the weaker the abstraction. And it's a powerful quotation. You have to unpack a little bit. But what it just says is focusing on the essence is more useful, right? It's just like I talked about the Unix file API. There's a limited number of calls that allow you to do a lot of stuff without thinking about the details, right? And if we start having to put more and more stuff into it, it becomes more complicated and it becomes less focused on its essence. I had an example at work where somebody has, they've defined from the provider side an interface with 40 methods. So here's an example. If I need to mock that for a unit test, I've got to create 38 dummy methods because I only care about 2 of them, right? And in fact, my entire program only cares about 2 of them. It's an interface that represents something I can query across the network, and I only use 2 of the queries. So in theory, I should have been able to define an interface that provided the 2 functions I cared about and not had to dilute it with the other 38 I didn't. All right. And that leads to number 4. And number 4 is, again, by starting off with small interfaces, when and if we need something bigger, we can compose them. And we've seen this. I can take the reader and the writer, put them together, get a read writer. I can add a close and I can get a read write closer. And there's uses for those, right? So start small and compose if needed. All right. Now, 5 and 6 are a little different. 5 is more a general issue in object-oriented programming, right? I want my interface to describe abstract behavior, and I want to avoid putting things into my interface that tie it to a particular implementation. The purpose of an interface is to describe abstract behavior, and the more abstractly we describe it, the more useful it is. Okay, this last one I'm going to drill down to in a sec, right? Accept interfaces, but return concrete types, with a couple exceptions. And this is again about consumers. If you're returning a value from your function, then I am the caller and I call you, I consume what you return. I should have the maximum freedom to decide how to consume it. Okay, so let me drill down into that because I think that's worth an illustration. And there's a quotation which is in some form been around in networking for a long time. This idea came up during the formation of the internet. When you talk about internet protocols, right, and you have parameters and maybe optional parameters, and the idea is, you can be liberal in what you accept. So you're sending me a message and you send me an extra optional parameter I don't care about, I ignore it, okay? But I'm careful about what I send back to you because I don't want to assume that you're going to accept more detail from me than you know how to deal with, right? So be liberal in what you accept and conservative in what you send back or return. And that comes down to 2 points. So the first one is, we want to accept an interface, and ideally a minimal interface, as a parameter coming into a function, because that allows the caller the maximum freedom to pick a concrete object to satisfy that abstraction. Okay? So if we only need to read, then specifying that we want a read write closer is not very good because we're demanding something that has functions we don't need. It would also be bad if we said, hey, give me an os.file. Well, I don't need an OS file, I need something I can read from. So again, by accepting the reader interface, for example, I've defined the minimal behavior that I must have and given the caller the maximum freedom to choose what actual thing to pass in. And you say, well, you know, if you know you're reading from a file, who cares? Yes, but when I go to write unit tests, I might not want to read from a file. When I go to write unit tests, I might want to call your function with a buffer. And I have the freedom to do that because I can create a buffer, and that's a reader, and you'll read from it not knowing that it's not a file. So the second point is similar, but it's from the other perspective. Okay, it has to do with how do I, the caller, consume what you return to me. If you return to me an interface like read, write, closer, you're demanding that the only way I can use the thing you've returned is to read, write, and close. But let's suppose you're actually creating a file. Well, then give me the file pointer, because maybe I want to do something else. Maybe I only want to read, but maybe actually I also want to be able to do a stat function and get some data about the file through stat, right? Well, if you give me a read, write, closer, I can't do that, because I can't do anything other than read, write, close. So if you're restricted what I'm doing with what you're returning. Every rule has an exception. And the exception here is returning error, because we just had this example. The one mistake is returning a nil concrete pointer in like the error interface, because the error interface is not nil, but the way we handle errors is by asking, is the interface nil? And nil in the nil interface sense, not in the nil pointer sense. Okay, so when you're returning errors, return the error interface. Okay, but the rest of the time, prefer to return a pointer or just a value, a concrete value, not an interface. So the last thing I want to say about interfaces, and there's another Rob Pike quotation, you know, the empty interface says nothing. Okay, because an interface with just empty brackets has no method set. So what behavior does it define? Well, it's not restricting behavior to anything. And so literally, the empty interface can be anything. An integer, a floating point number, a string, your own struct type, whatever. And in fact, this is very powerful because this is how we do a lot of stuff with reflection. If you look at something how like printf is declared, printf takes its printf, the string, and then what it takes is a list of arguments. Now, I haven't talked about variable argument lists. I'll get to that later. But what's in that variable argument list? Well, it's the empty interface. It's anything. So it doesn't matter what I pass to printf. I can pass an int and a string and a struct and a slice, whatever. Okay? In a sense, the empty interface is like the void pointer in C or C++. Okay? It can point to anything. So we're actually into the realm of dynamic typing when we use this. And the way we get out of this, of course, once I'm in the empty interface, what methods can I call on it? Well, none, because it has no methods. And so that's why we have to use reflection, okay, to look at that interface type, right? So if you give me one of these, this any type, I'm going to have to use reflection to find out what's really in it to deal with it. And again, reflection is something we're going to talk about in a later segment. Okay, so that wraps up my third segment on object-oriented programming. I wanted to talk about how interfaces work so I could describe what the nil interface is and why sometimes the nil interface trips people up, particularly with the use of errors. I wanted to talk about pointer and value receivers again, how they work, and so that particularly led us into how method values work. And we'll see method values some more, particularly when we get to the next homework problem. And then I wanted to talk a little bit about interfaces in general, how to use interfaces or how to think about using interfaces, and the empty interface, which will also come up a good bit.